Today we are talking about correlations and regressions. And hold on, let me change the settings on the meeting real quick. So today is where it gets a little bit more complex. So rewatching the lecture video is probably going to come in handy. I'm going to try to squeeze this in as close to an hour as possible, but I definitely think we'll end up going over. So if you have to leave, all good. All right, so we kind of ended the last lecture looking at this scary flow chart, which is our decision tree for basically the first half of the semester. So kind of up, like if you drew a diagonal line from here to here, this is going to be the exam 2. We're not going to do clinical measures or chi-square in this class. And then ANCOVAs, factorial ANOVAs, and MANOVAs are going to be exam 3. So understanding how this tree works and how you're going to select your tests based off of variable information is really important for you to kind of keep straight. For all of the tests we run in this class, the dependent variable is always going to be parametric, okay? Parametric meaning ratio, okay? So parametric or ratio data are kind of synonymous now. When we look at our independent variable, it's also going to be parametric, okay? And this is specifically in the case for regression and correlation. So when we say parametric or ratio type data, we're working with quantities, right, that have been measured. So numerical values that are actually measured data, such that 0 would mean we have an absence of a measurement, okay? So we'll talk about correlations first. I think they're a nice building block into regressions. Most of you have heard of a correlation before, right? It's just a relationship between a given number of variables, right? So we can talk about a bivariate correlation, which is going to be when we have 2 variables, right? One independent variable, one dependent variable. We can have a multiple correlation, which we'll expand on in a little bit. That's when we have multiple independent variables and a single dependent variable. So in either case between bivariate or multiple correlations, we're going to have one dependent variable, right? The thing that kind of dictates if it's bivariate or multiple is the number of independent variables, okay? We'll then kind of touch on partial correlations. This is going to be where you have 3 or more variables in which you're excluding certain portions of independent variables. And this will come in when we start to talk about coefficients of determination and covariance. Those words don't mean anything right now, but they will. Okay. So when we talk about correlations, we denote a correlation using the coefficient R. We call this Pearson's correlation coefficient in short, okay? And R is only going to be indicative of linear relationships. Some variables might have curvilinear relationships. If you think about various other graphical sequences, right, there you could match relationships pretty much in any form. But what we're interested in this class in only is linear relationships. So within that, R can vary between -1 and 1, okay? 0 being in the middle. So 1 on either end is going to represent a perfect correlation, okay? And we'll see some pictures of this in a couple of slides. So the actual numerical value, and this is a highlight here, right? The numerical value of the correlation, 1, -1, 0, anything between any of these numbers is going to determine the strength of the correlation. The actual sign is going to determine the direction. Okay, so if we have a +1, that's going to be a perfect positive correlation, which has a specific direction based on the positive. Okay, negative or a perfect negative correlation will be a complete inverse of a positive correlation. okay? As, R of 0 would indicate we have no relationship. So this comes in handy, or comes into play when we talk about the null hypothesis for correlations, right? Because usually null hypothesis would say there's no relationship. So whenever we look at a null hypothesis for a correlation, whether it be bivariate or multiple, R is equal to 0 in the eyes of the null. Okay. So we'll start with bivariate. Start it off simple. Okay. This is basically how we look at correlations, right? We've done this a little bit in some activities prior to this where we've made scatter plots and we're like, well, does there seem like there's some relationship that exists between two given variables, right? Remember that when we plot variables, the independent variable is on the x-axis versus the y represents the dependent variable. Okay, so excuse me. These four graphs are examples of positive correlations, right? Where a direct increase in one variable is linked to a direct increase in another variable. But you can see here that the data can be spread, right, at various degrees. And this is going to be what our strength is, right? So a perfect or a perfect relationship would be 1. Strong relationship is anything between 1 and 0.7, right? So if we drew a line between these, right, how tightly would those data points hug that line? Okay, a moderate positive correlation would look something like this and would have an R between 0.7 and 0.3. And then a weak correlation, you can see the data points are a lot more spread out, right? And that would be between 0.3 or 0 being no correlation, okay? On the flip side, if we have a negative correlation, right, that's going to indicate a downward slope. So that's where we have, as we increase in the x direction, we're actually decreasing in the y direction. So two variables that are indirectly related to each other. But you see similar trends, like again, if this is a perfect correlation, right? If we kind of map that perfect line between all of these scattered data points, right? How tightly do those data points hug that line, right? The more spread out they are, the weaker the relationship is. And then in the case of no correlation, you can see there's no general pattern where we could say, oh, as x increases, y increases, or as x increases, y decreases. We can't really give any defined relationship. So that's where our slope is 0, or we say there's no correlation. Okay, so we will use correlations when we want to establish unknown relationships, right? So this is kind of a good starting point when maybe you're trying to see if a certain measurement is related to a given outcome, right? It can also be used for validating different protocols or equipment, right? Examples, if we're looking at, what's it called, body composition, right? Or we're measuring percent body fat. We can look at body composition by using skin fold measurements or bioelectrical impedance, right? So we could see how closely these two things or two tests are going to measure body composition by looking at how closely related they are. We can also see how well a test might predict performance, and this is the hint into how correlations are integrated into regressions. But we primarily would use correlations in a predictive way when we use cross-validation sets. And you guys get an example of this in the activity this week. So basically what you're doing is after you build a regression equation, which again we'll talk about in a bit, you would use a cross-validation data set to compare actual measurements, right? And compare those to predicted measurements And then you would use the correlation to see how close actual measurements are to predicted measurements. Okay. But like I said, we'll kind of get to that when we start talking about the regression area. I think a big takeaway from the lecture, though, is that correlation does not prove causation. You might have heard this phrasing before, right? Because you're proving if there is a relationship between variables. In the form of statistics, we're trying to prove if there's a significant relationship or not. But the big thing is that we're not proving a cause and effect relationship. We're just saying a relationship exists. Okay, and to kind of further expand on this, we could use an example of, say we were looking at IQ as an independent variable and GPA as a dependent variable, right? So does IQ predict, or can we say that if someone has a high IQ, they're going to have a high GPA, okay? While this may be true, right, or we could say that these are positively correlated to one another, there's also a lot of other things that might contribute to a student's GPA, right? Could be if they're highly motivated, if they have good study habits, if they have good financial support, right? If someone doesn't have a lot of money to pay for school and they have to take an extra job, that takes away from their study time, right? Which also is another factor, right? Study time, study habits kind of are hand in hand. Also depends on the instructor, right? If you have a good instructor, you're likely to perform better in class. This isn't always the case because, like I said, there's a lot of other factors that play a role in here, right? It also could be parental pressure if, like I came not from a fully Asian household, but there is a certain degree, I don't know if any other Asians are in the house, but yeah, there is a certain degree of pressure that comes from the parents on performing well in school, right? So we can see if this is the original relationship we wanted to look at, like looking at how IQ relates to GPA, we kind of have to take it with a grain of salt because we're not considering all of the other potential factors that could be contributing to changes in GPA, right? So correlation does not prove causation. So when you guys are writing your null hypotheses, we are saying there is no relationship. We're not saying there is no effect. Okay, so relationship, not effect. Okay. Another example is if we look at leg length versus pant length, right? Let's say leg length is our independent variable and pant length is our dependent variable. Typically, we could say people who have longer legs will tend to have longer pants. That makes sense, right? But we can't always flip it the other direction, where we say people who have long pants are going to have long legs, right? It's not a measurable thing, and it's not really realistic to ask people to grow their legs, right? So again, correlation does not prove causation. I just really like this example because I love that cat. But anyways, do we have any questions so far? We're looking good. Okay, so like I said, we use scatter plots a lot of times to plot out these data pairs between our independent and dependent variables. Okay, so scatter plots are going to be a good visualization for looking at correlations. In this scatter plot, doesn't matter if it's weak or strong or perfect, positive or negative, we can apply this line of best fit, which is something that I was kind of hinting at in the previous slides. Okay, so this is a linear estimate of the relationship. Okay, and the slope of that line is R. So in a bivariate correlation, right, let's say we're looking at this strong positive, we plot all of our data pairs. So what would you get if you have a certain independent variable value, and how does that, pair up with a dependent variable value? So that's what these points represent, right? And then we put this trend line, or this line of best fit, down the middle of all of these different data points, and the slope of this line is the actual bivariate correlation. Okay, now this is important to remember. R is the slope only in a bivariate correlation. Okay, when we get into regressions, the slope is going to change. Okay, but the line of best fit we can use because it has, every line has an equation, right? And we'll kind of get into that with the regression portion. But if you remember from grade school or high school, right, the equation of a line is y equals mx plus b, where m is the slope, right? And m is going to represent the change in y over the change in x, right? Or rise over run, if that sounds familiar. Okay, so that's also another thing to keep in mind as we move forward. Okay, so when you look at an equation of a line, if m, or the slope, is positive, that's indicative that we have a positive relationship, right? Or just positive, these two here. Okay, if the slope is negative, that means we have a negative relationship. Okay, if there is no slope or the slope is 0, indicative of no correlation. Okay, so the big question is how do we determine what R is? You guys do not need to know this formula. That would be way too much of me to ask for you. Okay, there's a lot of formulas that come out of this lecture. You don't need to know this one. But I do think it is important that you understand how R is derived. Okay, so as you can see, Z's, we've seen those before. Okay, Z is, remember, represents a distance, or a raw score's different distance from the mean, right? Remember, it's in units of standard deviation. So basically what we do is we take, remember, the slope is the change in y over the change in x. We're looking at what is the distance of y from the mean, what is the distance of x from the mean. We take all of the data pairs, and we do this for every single one of them, and then add those products together and divide by the numbers of pairs of scores, which ends up being however many subjects we've collected. Okay, so that if you look, a correlation is looking at the direction and size of deviation from the means for two variables. So this is how z-scores relate to correlations. And here's a pictorial representation, just in case this doesn't make sense. Okay, so let's say we have two variables, right? This is our independent variable, this is our dependent variable. Each of those variables is going to have a mean, right? And wherever those means line up, we would say is kind of like the master mean of our data set. I made that up, but that's going to be kind of our central location, okay? On each of these axes, we have, if you think about them as individual distributions, right? Below the mean, we're going to have negative z-scores, and above the mean, we'll have positive z-scores. So the same would go for the y-axis, right? Anything below the mean is negative, anything above the mean is positive. Again, in terms of z-scores. Okay, if we pick a point on this graph, I chose this one, okay, how we calculate R is we look at how far away is it from the mean in the x-axis, right? So if we draw a dotted line, right, we could say, oh, from about here to here, whatever that z-score is what would go in this area. So that's the change in x, okay? Then we say, where does this point land in the distribution of our dependent variable? In this case, we see we have a negative z, right? So that would be the distance defined, right, of this point away from the mean of whatever our dependent variable is. So to find the slope, right, we take the change in y over the change in x, okay? Or in this case, we're taking a product of the differences or the distances of our point from each axis or each variable's mean, right? And a negative times a negative is a positive. Oh, look, we have a positive slope. That makes sense, okay? If we were doing this for a different point, let's say we chose this one up here, it's pretty much the same concept, right? We say, how far is this point from the mean of x, right? Or our variable x, or independent variable. So we'd say, all right, it looks like it's a positive z-score, distance from the mean, right? And then if we look at where it's related to on the y distribution, right, or a dependent variable, we also notice a positive z-score. So that would also be a positive z distance from the mean of variable y. So again, if we're taking a product of these two z-scores, we still get a positive r. And so by doing this with every single little dot on this scatter plot, we can take the sum of all of these products, we divide it by n, and that's how we get our correlation coefficient, okay? We can do the same thing if we're looking at a negative distribution, right, where we pick some random point, determine how far away it exists from the mean on the x distribution, how far away it exists from the mean in the y distribution. We take the product of those scores, right, where we have a positive in the x variable but a negative z in the y, and we get a negative slope. Okay, so that's how this r, or this line of best fit, or the slope of the line, is determined. Did I lose anybody? I'm going to take that as an kind of, but generally a no. Okay, so when we put this in a computer, it's so much nicer because the computer does all of that work for us, right? So when you guys are working in SPSS, you're basically going to input two sets of data, one set for your independent variable, one for your dependent variable. If you have multiple variables, you'll put all of them in, right? And then SPSS is going to do all of this beautiful calculations for you, okay? So what I do want to point out, though, is there's a denominator of this computer calculation that represents covariance, which is an important topic that we're going to talk about today. So this covariance indicates how much x and y vary together. We also refer to covariance as the coefficient of determination, okay? Again, you don't need to know this equation. You don't need to know this equation, okay? But covariance, if you kind of look back at what our actual variance equation is, it's quite similar, okay? So covariance, basically, we also refer to as coefficient of determination. It's r squared. Super easy to calculate. If you know what r is, you can figure out what the covariance or coefficient of determination is, okay? Basically, what this represents is the common variance or shared variance, right, between two variables. So what the heck does this mean, okay? So let's give an example. Let's say we have r as 0.7. So this would be a strong positive relationship between two variables. If we square that, we get 0.49, okay? If we translate our coefficient of determination or covariance into a percentage, basically we read that as there's 49% of the variability that we notice in the dependent variable is explained by the independent variable. So you can imagine as r gets stronger, our r squared value will get larger, right? So if we had 0.9, we would be able to explain 81% of the dependent variable, okay? Whatever the leftover percentage is going to be the probability that the relationship is due to error or chance or other factors. So in terms of our example looking at IQ versus GPA, let's say that our correlation between IQ and GPA gave us an R of 0.5, right, may be relatively moderate, right? So that would translate into R squared, which is a 0.25 or 25%, right? Or if you think 5 squared is kind of an easy way to think about that. So 25% of the variability we see in GPA would have been explained by its relationship with IQ, right? The other 75% of the variability we see in GPA would be due to all those other factors we listed in that slide. Okay, so R squared is, or the coefficient of determination / covariance, is going to be how much of the dependent variable is related to the independent variable we're investigating. And remember, it's not that the independent variable is causing variability within the dependent variable. It's just that we can say, based on their relationship, it's sufficient to say that a certain degree or certain percentage could be possibly caused by the independent variable, okay? So a nice way to look at this is through Venn diagrams, right? If let's say this is A is our independent variable, B is our dependent variable, right? We can look at the area of overlap to figure out what the coefficient of determination is, okay? So again, this is the probability that the dependent variable is explained by variance in the independent variable. So if we have 0 overlap, that means there is no relationship between these two, right? Because if R is 0, R squared is going to be 0, okay? If we have total overlap of both of these variables, that means R is 1, right? Because R of 1 would mean an R squared of 100%, okay? So anything or any type of overlap or degree of overlap in between is going to be anywhere between 0 and 100% for R squared, okay? So when we talk about hypotheses, I'm sorry if I'm moving a little bit fast. If you have a question, please ask. Okay.
Sorry, could you go back and explain why R is 1 in the last slide? This one?
Yeah. So if we're comparing two variables on separate levels, right, and we want to see what their relationship is, if we notice that they have a full overlap, right, that means that all of the variability we see in circle B is explained by the variability that lies within circle A. Okay, so that would mean that as A increases, B increases the exact same amount. Or vice versa, it could be a decrease if it's a negative correlation. So in that case, we would have a perfect relationship. Could be positive, could be negative. But if there's a perfect relationship where both of these line up on top of each other, then R would be 1, R squared would be 100%. Did that make more sense?
Yeah.
Okay, cool. Okay, so if we talk about statistical significance, which is why we are here, right, we're talking about p-values, okay? So remember, in our class, we're always going to talk about a two-tailed test with hypotheses, okay? So in this case, remember, if R is representing a correlation or a relationship, we're going to say there's no correlation or no relationship between variables for the null hypothesis. In other words, R should be equal to 1, okay? You as the researcher are always trying to prove something different, right? So your research hypothesis would be that they're not equal, right? So R might be a positive correlation, or it could be a negative correlation. We don't really care what the direction is. We just know that the research hypothesis is going to say there is a relationship between variables, okay? When we evaluate this with p-values, remember the p-value is the probability that the null hypothesis is true, right? So the bigger that p-value, the more likely it is that the null hypothesis is true. The smaller that p-value, the less probability that that hypothesis is true, right? In which case, if it's small enough, we say reject the null and we accept new relationships, right? So in this process, we're going to start getting into using critical values. If you have the book, there's a correlation coefficient table. We don't use this one in the class, but I can kind of show you how it works. Generally, SPSS will let us know when we have significant relationships. So for any type bivariate or what do you call it, multiple correlations, SPSS does all the work, okay? Basically, you just have to identify where there are asterisks, okay? And the asterisks, I hate that word, asterisks will tell you where the significant relationships exist in whatever you're measuring, okay? But the correlation coefficient table kind of looks like this, where we have some degrees of freedom on the side, which are going to, again, be related to how we kind of make that correction factor for the sample always being smaller than the population, okay? And then these values in here represent critical values, okay? So up on the top, you'll notice these slightly familiar looking values, right? Particularly 0.1, 0.05, and 0.01. These would line up with a 99% level of confidence, a 95% level of confidence, and a 90% level of confidence, right? In other words, these are our alpha values. So you, the researcher, again, before you run your statistics, you say, I want a 95% level of confidence, okay? So based on the degrees of freedom that exist, basically this means your sample size, right? Let's say we have a degrees of freedom of 20, and we're working with a 95% level of confidence, okay? The value on this table is 0.4227. So this critical value indicates how big your correlation coefficient has to be in order for it to be significant past 95% level of confidence, okay? So if your correlation was 0.43, you would have a significant relationship with a degrees of freedom of 20 at 95% level of confidence, right? If your correlation coefficient was 0.420, that would not be significant, okay? Because you didn't meet the criteria to be significant. So these tables, we're not going to use this one, but we will use a t-distribution, which I'll bring up later in the lecture. And then in a couple of weeks, we'll start using an f-distribution. That's about as far as we go in this class, but they all run off of the same concept, okay? So in this case, when you're using R, right, in the table, N usually is going to represent how many subjects you have, in this case, how many pairs of scores, which means the same thing as the number of subjects, okay? But remember I told you when we first had our first lecture on degrees of freedom, we used an n-1 in the standard deviation and variance equations. And I told you degrees of freedom is not always going to be n-1. This is the first example where degrees of freedom is not n-1. Okay, so in a bivariate correlation, when we use this critical value table, or in other words, SPSS does all the work for us, it's going to automatically identify how many variables are we looking at, and it'll take 1 degree of freedom away for each variable that we use. So in a bivariate correlation, it would be n-2, because there's 2 variables, right? If we were in a multiple correlation, it would be, again, however many variables were being compared, okay? One thing I do want to note for p-values for correlations is that the p-value only tells us about the significance of the relationship, okay? So if you get a p-value less than your set alpha, you say it's a significant relationship. If you get a p-value greater than your set alpha, it's not a significant relationship, okay? P-value says nothing about the strength of the correlation. So remember, strength of correlation is determined by the numerical value of R. The direction is determined by the sign of R, whether it's positive or negative. Okay, p-value says significant or not significant. All right. So that brings us to our null hypothesis for a bivariate correlation. Okay, it's a bit of a repeat. Again, our assumptions, and I have these summed up at the end of the PowerPoint as well so that they don't get lost in the PowerPoint. But remember, you're starting with one parametric independent variable, one parametric dependent variable. That's where we get this bivariate word, okay? Two variables. You have to assume that you've collected your sample via random sampling, and you have to assume your sample is normally distributed, okay? Usually in a research situation, it would be up to you to test for normality, but for us, we're just from here on out, we don't test for normality really anymore, so you're just assuming normal distribution, okay? So if we had a research question, right, basically it's investigating, is there a significant relationship between whatever our independent variable is and whatever our dependent variable is, right? Using a non-directional hypothesis or a two-tailed test, right? Our null hypothesis, written out in words, would say there is no significant relationship between the two variables, right? On the flip side, the research hypothesis says that there is a significant relationship. Reminder, your statistical tests are only going to test the null hypothesis. That's why I put it in yellow, okay? So of all of the hypotheses you remember, for all of your tests, always remember the null, okay? So for a bivariate correlation, no significant relationship, okay? Whether you reject or accept that tells you how to write it, okay? So you know one thing, and if you reject, it's just the opposite of what the null is. It's try to make it as simple as possible, okay? All right, for bivariate regressions, regressions are going to pull in correlations, okay? Bivariate still meaning we're working with two variables, okay? So regressions use correlation coefficients, okay? But we use regressions when we want to predict the value of a dependent variable based on a known relationship with an independent variable, okay? Typically that relationship has to be greater than 0.7, meaning it's a strong relationship. Otherwise, we can't really accept results, okay? We'll have various examples where this isn't true, but that's just for the sake of being able to create a lot of different examples in your activities. So regressions use relationships to help predict certain outcomes is a nice way of putting it. But anytime you see the word predict, think regression, okay? There it is in red, just in case you didn't catch it the first time. Okay. So usually we will perform regressions when one variable is harder or more expensive to measure than another, right? So example, we could estimate or predict VO2 max values from somebody's 1.5 mile run time. I don't know if this is actually done or not, but VO2 max requires quite a bit of equipment and time and people, right? You also have to be nicely rested because if any of you have taken a VO2 max test, that is a hard test, okay? So again, the key here is that you want to be able to predict a certain variable, okay? So similar to correlations, we have bivariate and we have multiple. Okay, we'll talk about bivariate regressions first. Bivariate regressions are also referred to as simple linear regressions. Okay, so again, we use these regressions, or we build regressions when we have relatively strong relationships, right? And we're going to be predicting variable y, or a dependent variable, based on a known relationship with an independent variable. Okay, so we're still using a line of best fit. This line is referred to as the regression line. What? Okay, so when we have a correlation, remember that the line of best fit is representative of the slope, or the slope of the line of best fit is the correlation, okay, which is a little r. Okay, when we're using a regression, the regression line is represented by a big R. Okay, and even sometimes the notation will be different. It might not be a big R, but rather it could be the letter B, which is what we'll use in this class. So I probably should have changed that. So if you want to write B instead of R, I think that would probably be a good idea, so you don't get confused, because big R comes into play when we talk about multiple correlations. So yeah, I would change this to B. Okay, but basically what we do is something kind of similar to correlations to get this regression line. So if you recall back to the graph where I was doing the z-scores, the distance from the mean, that type of thing, we do something similar for a regression line, where we say all of these different pairs of scores in a scatter plot, right? And we look at the residual. But the residual is a little bit different from our z-score calculation, because it's telling us what the vertical distance between the raw score and the line of best fit is only, okay? So the whole point of the regression line is to make sure the sum of the residuals is 0. So basically it's saying for all of the values on the lower end of a distribution are relatively equidistant from this line of best fit, as are data points that are at the upper end of the distribution, okay? This other point is that we minimize the sum of our squared residuals. This is more or less looking at variability. So the main thing I want you guys to know here is residuals, what they actually are, okay? Outliers can have a big effect on the regression equation, as you might be able to guess, right? The bigger an outlier is, the further away it's going to be from the line of best fit, okay? So if we look at a bivariate regression, right, or as far as our regression line is concerned, remember we said y equals mx plus b, right? That's generally the equation that you learn. I hate to flip this on you, but SPSS uses, again, b as a slope, okay? So when I went back to this slide and said regression line, think B instead of R, make sure you think B, okay? The book that I used for this lecture used R, SPSS uses B. So I apologize if there's any confusion, but from now on, B is going to represent your slope, okay? A, we can also call this B sub 0, is going to be your y-intercept, okay? So I've listed that here. A is your y-intercept. B is going to be the slope of the line, okay? This is going to tell us how much the dependent variable is expected to change given a change in the independent variable. So again, change in y over the change in x. You can think standard deviation or deviation in y over the deviation in x as well. But you can see R where the relationship between two variables does play a role in this calculation. However, when you're looking at a bivariate regression, R is no longer the slope. Okay, so we have, because we're adding in a prediction factor, B becomes the slope and R is integrated into the calculation of B. So a lot of times in a bivariate regression, if you're using like Excel to make a line of best fit in a bivariate correlation, the correlation coefficient oftentimes might be very similar to B, but this is going to change when we have multiple regressions or multiple correlations. So again, regression, slope is B, correlation, slope is R. Okay. So we have a visual representation of this as well. Okay. So again, we're looking at a positive correlation in this picture. Correlation, remember we said the line of best fit. Slope is represented by the actual correlation value. Okay. When we look at a regression, okay, the slope is B. So I, again, pound it out because it always gets confused in the semesters. Okay. Just to point out in this graph, this is what a residual is, right? The vertical distance from a given point to the line of best fit. Okay, so you can imagine something like this guy out here might be an outlier that increases the distance, right? And this line of best fit in a regression is made out of looking at the sums of the residuals put together, okay? So a larger sum in this direction likely would shift the regression line upwards, where if this point didn't exist, that line might not shift, okay? So outliers are bad always, kind of the main takeaway there. All right. Do I have any questions before I keep going? I'm so sorry. This one's hard. Yeah.
I have a line of regression starts from like y-axis.
Oh, that's a good question. It doesn't have to start from the y-axis. We just say any line between x and y variables is always going to at some point cross the y-axis. And that's where we end up getting our y-intercept. Okay, so in this one you can see B0 indicates where the y, or where this line of best fit would cross the y-axis. So that's your constant in your equation. So that would be like A here, right? So you can sub out B sub 0 for A if you want to. And then in this area, you can see the slope of the line is represented by B1. Okay, when we get into multiple regressions, there's going to be multiple B coefficients. So we'll use B for now. Did that help answer your question?
So what does the regression line tell us?
The regression line tells us for every change in X, we can predict a particular change in Y, given that we have some starting period. So I do this example in one of the videos that I shared with you guys, but I'm gonna, oh no, not mute. I'm gonna stop sharing for a second and I'll just show you, because I think this one kind of puts it into perspective a little bit better. But going to college is expensive, right? So let's say if we're making an equation, Y maybe is representative of your total cost of education, right? And maybe let's say tuition is usually what, like $4,000 a semester if you're like full-time, okay? And then let's say you have to pay $500 to enroll. I don't know, I made that up, okay? So $500 is kind of like our y-intercept, our starting point. okay? So I'm going to say y-intercept, okay? X would represent numbers of semesters, right? So in this case, this is our independent variable, right? Because we're interested in how many, or like, if I go to school for X number of semesters, how much am I going to owe in the end, right? So if we look at 4,000 as B, right, it's our predictive relationship. So that would be, this would be the slope of our regression line. Basically saying that for every year, right, if we're looking at a graph here, starting point being 500, right, with an x-axis, we're saying for every year, right, let's say this is, well, let's say these are semesters. So one semester would put me at $4,000, right? So for every year I go, or every semester I go to school, I'm increasing by $4,000, right? Let's say I go a second semester. From that point, I'm going to increase another $4,000. So now I'd be at $8,000, right? So that's how the regression line works, or B is going to represent the units of Y. So how much change in Y, right, or in this case, our money, how much cost are you adding on by adding incremental changes in X, in this case, semesters. Okay. Did that help make a little bit more sense?
Yeah, it did.
Okay, cool. Woo! Stats is fun. Tell it to yourself, guys. All right, so with this being said, last week we talked about standard error, kind of representing how far away a given sample value would be from a population value. You do not need to know this equation, okay? So the standard error of the slope, right? Standard error of B, because we're talking about regressions, okay, can be turned into a critical value by comparing it to the sample B, or the sample regression slope, okay? The way we evaluate this is through a t-distribution. So similar to when we were looking at bivariate correlations and we used the correlation coefficient R distribution and had certain critical values that would say your relationship has to be this strong in order to be considered significant. We're going to have a similar thing going on in the t-distribution where we have critical values at given degrees of freedom based on how many people we've included in our study and based on the existing relationship that exists in our regression, which is B, right? As well as whatever our level of confidence is, okay? And all of this is going to tell us what B basically needs to be. We turn it into what's called a t-statistic, okay? But basically we compare T to these critical values. Critical values are going to tell us how large does this relationship have to be in order to be significant, okay? So the way that we evaluate this on the table, a rule of thumb, is that when T, your calculated T, that's this guy here, is greater than the critical value that this is going to be on the table, okay? So T is calculated, critical value is on the table. The critical value exists at a given degrees of freedom and level of confidence, and I'll show you guys that in the next slide. But when T is greater than the critical value, we say it's statistically significant, okay? And what is statistically significant? We're basically saying the regression line is, right? Or the slope of the regression line. Remember, the slope of the regression line is an indication, right, of how well our independent variable is able to predict our dependent variable. So when we get a significant result out of this table comparison, we're basically saying that B, right, or the predictability of our dependent variable using a given independent variable is sufficient, right? Or it's statistically good to use. Okay, so when we look, I posted the t-table on your guys's Beachboard page, and you can use this for practice problems, which I posted a video for, and it goes more in depth on how to use the table, so I highly recommend watching it. But in this case, degrees of freedom, which is this column here, is going to represent the number of independent variables in the regression. So if you're looking at a bivariate regression, you have one independent variable, one dependent variable, okay? So one independent variable means you're taking n minus 1. If you have a multiple regression where you've got maybe 5 independent variables, it would be n minus 5, okay? So degrees of freedom are going to change based on the number of variables you have, specifically independent variables. Okay, but again, I go through how to read the table on the video really, really well. So for sake of time and getting to our other topics in the lecture, I'm going to kind of skip ahead. So when we look at a bivariate regression, again, our assumptions are that we have a parametric independent variable as well as a parametric dependent variable. We have random sampling, normal distribution, all that good stuff. Okay. Remember that the purpose of a regression is to predict, right? You use an existing relationship to predict if that relationship is significant enough, right, to predict a dependent variable. Okay, so again, non-directional hypotheses would tell us the relationship between the independent variable and dependent variable is not significant enough to predict the dependent variable. Okay, again, that predict is an important part of the null hypothesis for a bivariate regression. Okay. All right, we can also calculate confidence intervals for the regression. This should look kind of similar to our confidence interval for a true mean of a population that we used last week, right? Instead of z, we're using a critical value at t, okay? And instead of a standard error of the mean, we're using a standard error of our slope of our regression, okay? One thing I want to highlight is t does not equal the calculated t that you find using this equation, okay? They are different. So if you're trying to find t when you already know degrees of freedom and your level of confidence, okay, and you're trying to see if you have significance, that's when you calculate t. When you're trying to find the confidence interval, given a level of confidence, you have to say, this is the critical value that exists at this level of confidence or at this alpha level, right? And then you multiply that by the standard error and then plus or minus whatever the b is. So I've given you guys some examples or practice problems to work on. There's I think it's like 20 minutes of a video that goes through how to do these. And what I did is I ended up changing it so that you're determining significance for 1, 2, 3, 4 problems, and you're also determining the confidence interval for 1, 2, 3, 4 problems, okay? But you're going to use the equations that are provided in the 3 slides previous to this, okay? So, yes. From here on out, that's kind of the bulk of the lecture. If you understand the bivariate stuff, the multivariate stuff is just adding a few terms and some more variables, right? Because the difference between bivariate and multiple correlations and or regressions are that you have multiple independent variables. So that's pretty much the only thing that's changing, okay? So let's see, I don't know why I wrote that. So multiple correlation coefficient, this is why I said instead of capital R on the regression line, put B, because the statistics book, which I think is kind of dumb, uses R for both, and that's just really confusing. So the easiest way to remember it is bivariate correlation is a little r, multiple correlation is a big R. Okay. SPSS doesn't differentiate between bivariate and multiple or multivariate correlations, so it always uses a big R. So if you just want to keep the letter R in your pocket for correlation coefficients, that's totally fine. Okay. But like I said, all we're doing is we're considering more relationships with a given dependent variable. Okay. Again, your R value can range anywhere between 0 and 1, right? And this could be 0 and +1, 0 and -1. It's all with regards to the relationships that exist between variables, okay? Similar to our coefficient of determination for a bivariate correlation, R squared means exactly the same thing, right? How much shared variance do we have between an independent variable and a dependent variable? Okay, so that percentage concept crosses over. So all of that is the same for a bivariate correlation, okay? Like I said, the only difference is more independent variables. So if we're looking at a null hypothesis for a multivariate correlation, oh, by the way, any of the slides that look like this are probably good to either filter out of the lecture notes or to write down somewhere else, because these are helpful, or they will be in the future, okay? So our hypotheses, again, we have parametric and independent and dependent variables, random sampling, normal distribution, woo, 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 okay? But instead of, again, researching relationship of, or the relationship of a single independent variable, we're now looking at relationships between multiple independent variables and a single dependent variable. So again, basically what happens in a multivariate correlation is you look at individual relationships of a whole bunch of different variables. That's all it's chalked up to. It's not really that much more special than a bivariate correlation, okay? The only difference is that in order to calculate multivariate correlations or multiple correlations, we have to use partial correlations. Okay, so how does this work, right? We look at a bivariate correlation between, let's say, our dependent variable, which is the blue circle, and independent variable number 1, which is my white circle. Okay, let's say that relationship, or R, is equal to 0.45. Cool. Okay, so that was our area of overlap, right? Now let's say I look at a relationship between my dependent variable and variable number 2, which is my red circle. And let's say that relationship is represented by an R of 0.45. So that would be my area of overlap as well, okay? But you can see that there is some degree of overlap between variable x1 and variable x2, okay? What partial correlations do is it excludes this overlap area between x1 and x2, okay? So by doing that, we end up isolating any given part, right? So it would basically be, if I wanted to know the pure relationship between variable 2 and my independent variable, I would have to take the area of overlap that exists, or the covariance that exists between these two variables, and subtract it from the total area of overlap that exists between variable 1 and the dependent variable, okay? So partial correlations end up giving us this little value here, and that's what multiple correlations, it's kind of the major difference. But like I said, in SPSS, basically what you get is this thing called a correlation matrix. And what it does is it just lists all of the bivariate correlations that could possibly exist for a given pairing based on the variables that you're measuring. So let's say that my dependent variable is isokinetic torque. Sure, right? And we want to know, how does this variable change, or how could we how does this relate to other independent variables such as age, fat-free weight, height, weight, BMI, fat, etc. Right? You'll see on this matrix though that the top portion is empty. Why is that? Because it's exactly the same as the bottom portion. Okay. So when you make matrices or matrices in Excel, you guys will practice doing this, but you only make the bottom portion. If you're doing it in SPSS, this top portion is going to be included, but you only really need to read the bottom portion, okay? Because they're redundant with each other. The other thing to note on this matrix is that the values on this diagonal all have a perfect correlation. Why? Because they're correlated with the exact same data, okay? So if I have ages listed from my sample and compare them with the same age list, it's going to be a one-to-one relationship, right? If subject 1 is 15, if they're getting compared to the same age list, 15 and 15 are going to pair up in the same spot on a distribution, okay? So when we read the matrix, we ignore these perfect correlations, but these are kind of our dividing line between the redundant values on the top and the bottom, okay? The bottom row, in this case, if isokinetic torque is my dependent variable, the bottom row will display the bivariate correlations that exist between each independent variable and my dependent variable, okay? This can change based on how you organize the table. But in this example, these would all be basically representative of the multiple correlations we're looking at. Okay. So, well, headed into the last stretch here. Multiple regressions. We basically use these correlation matrices to build multiple regressions, okay? So similar to how we use bivariate correlations to make bivariate regressions. Again, the only difference is you're now using multiple independent variables. Again, the purpose of a regression is to predict a given dependent variable. So if a bivariate regression has the equation of a line of y equals b sub 0 plus b1 times x, right, where b sub 0 is our y-intercept and b is our regression line, or our slope of our regression line. Basically what we do is we have a lot of slopes of regression lines, okay, because we have multiple independent variables. So again, each b is going to be the weight or strength of each independent variable's line of best fit. So in a multiple regression, we technically have a lot of different lines going based on a relationship that exists between an independent variable and a dependent variable. And again, this b value is going to be different for each independent variable, okay? Because it's going to be based on the units that are going to be changing. So when we look at our null hypothesis for our multivariate regression, same assumptions, okay? Random sampling, normal distribution are base assumptions that go with every test we run, right? But we're primarily looking at if relationships between two or more variables, which is going to be all of our b values, right? Are those b values significant enough to predict a dependent variable? That's kind of the base of what we're looking at. So the null hypotheses generally are going to be the same as a bivariate regression. because we technically are testing one B variable at a time. Okay. Woo! All right. So then, there's more. There's different ways that we can organize a regression. The first way is called the hierarchical regression method. So this is going to be indicated as enter in SPSS, and there's an example of this in the lecture or in the activity this week. But that's going to be where you, the investigator, choose the order in which independent variables are inserted into a model. Okay. And this is going to be based on several different factors. So it could be based on the reliability or the validity of one test over another. It kind of just depends, okay? But it's you, the researcher, choose the order. That's kind of the big takeaway of hierarchical method. Forward selection, I go into deeper detail on this in the flowchart videos, which are in the supplemental resources section. Use the flowcharts, guys. They have been, I posted this in the news item today. This, I swear to God, flowcharts were the most helpful tool according to students on their spot evals. And I have had really great students in the past. Usually everybody fills in the written sections of their spot evals. And flowcharts, other than memes and GIFs, everyone loves memes and GIFs, but the flowcharts were the #1 contributor to learning in the class. So I put blank ones, I put filled out ones, use them as practice to make sure you understand how to read things and that you're understanding, one, how to read the outputs, but understanding how these methods work. Because I do one for forward selection and I do another one for backward elimination. But basically, I'm going to give the dummy down version of forward selection in the lecture since I go deeper into it in the other video. But the whole idea of multiple regression is you want to try to get R squared as high as you possibly can, okay? And remember, R squared is the shared variance between independent variables and the dependent variable. In a multiple regression, we just keep adding R squared, okay, based on the independent variables that we're investigating. So the higher R squared is, remember, R squared is translated into a percentage, right? The higher R squared is, the more of the dependent variable we're predicting. So in any of these, particularly forward, backward, and stepwise methods, we're trying to get R squared as high as we can get it. So with forward selection, the base concept is that you start with no variables in your model, and then you add variables to the model one by one, and see if they increase R squared significantly. Once you start seeing non-significant increases in R, you don't need to add to the model anymore. So that's kind of like very, very basic forward selection, okay? For backward elimination, it's the opposite, where you start with all of the independent variables in the regression model, and then you take one away, one at a time, and see, well, did that elimination decrease R squared significantly? If you have a big decrease, that's not good, right? Because again, we want R squared to be as high as possible. So if you take a variable out and it decreases R squared significantly, you have to put it back into the regression. If you take a variable out and it doesn't decrease R squared significantly, you can keep it in. So that's basically what all these words say, okay? And again, video, super, super helpful. Those are hierarchical, forward, and backward are going to be the three main ones that we use in this class, okay? Stepwise, it's debatable if this is a good method or not, but it follows the same starting procedure as forward selection, where there's no variables in the regression model. And then as we add in independent variables, we can remove them if we don't think they actually contribute good. So the example I use with this one is like when you get dressed in the morning. Let's say you're butt naked because you like to sleep naked. Sure, I don't know, right? So you get out of bed. The first thing you put on is something that covers the largest surface area on your body. So let's say your legs take up the largest surface area on your body. So you're going to say, I'm going to put pants on first, okay? And then you're like, all right, I need to add to the covering of my body, so I'm going to put on a t-shirt, right? But then you reevaluate, you're like, crap, I forgot my underwear. So in this case, you've added independent variable of your pants, you've added independent variable of your shirt, but you have forgotten said underwear. So in that case, we've added two variables, but now we can remove one. I just realized I chose the wrong finger to remove. But we can remove your pants, right? Take those out, put in another variables of underwear. And then if we think, oh, I think pants were still valuable, we can put pants back in, right? So it's this stepwise method of adding in variables and then removing some and then adding some back in until we feel like R squared is significant, okay? This is a more complex process, and it, like I said, it's debatable on if it actually gives good results or not, but those are the methods in which we use to do multiple regressions, okay? So again, the whole point of a multiple regression is you're trying to build the best equation possible using known relationships between independent and dependent variables, and you're trying to see, does this equation give me the highest covariance or the highest percentage of predictability possible? That is the multiple regression in a nice summed phrasing. Okay, you guys are probably sick of me talking by now. We're almost done, I swear. Okay, multicollinearity. So now we're kind of getting into special notes for things. Okay, multicollinearity is going to occur when you have two or more independent variables that are strongly correlated with each other. Okay, so in an example that I gave earlier, we had mass, fat-free mass. This is no bueno. Obviously, we can expect these values to be somewhat correlated to mass because they're a part of the calculation for mass, right? Similar concept exists for BMI. Height and mass are part of the BMI calculation. Therefore, we know there's going to be a relationship based on how that calculation is made or organized. So when we have this multicollinearity, it can sometimes skew our regression results because it's almost like we're counting some values more than once. Not that great, okay? So singularity is a form of multicollinearity, and it's going to occur when you have a perfect correlation between two independent variables or combination of other variables, okay? So let's say height and BMI were perfectly correlated. That would be an example of singularity, okay? So in that correlation matrix, usually that we kind of use those bivariate correlations to make that regression model. If you see any perfect correlations other than the diagonal line across the center of your correlation matrix, that's a red flag, okay? So multicollinearity, we don't really want that in our regressions. And I do realize in the activity, there is an example of multicollinearity, but it's for the sake of the example for the activity. So we don't actually test for this in this class, just know that it's a bad thing, okay? And that it's an assumption. We have to make sure we don't have multicollinearity when we're running regressions, okay? All right, special notes. Similar to bivariate regressions, we can still calculate confidence intervals. We're not going to do that for this class because it gets really complicated. There would be a lot of confidence intervals for a lot of different B slopes, okay? But it still can be done for a multiple regression. Similar to other conversations that we've had previously, the larger your sample size, the better. And this is going to come into play when you use different methods of collection. Okay, so usually we say you want about 20 subjects per variable that you're adding to the regression. So if you have 3 independent variables, you would want at least 60 subjects. That's kind of the rule of thumb. Okay. If you're doing a stepwise regression, because of that add and subtract characteristic, you usually want more people. So we usually say double, which is why, again, stepwise regression, not the best method. Okay. And then we get this cross-validation concept, right, that I kind of mentioned back in the beginning, where once you find a model, you have to see if the model works. So what you do is you take, let's say we were measuring body fat, right? We use a sample to create a regression model to predict body fat. We then have to use a cross-validation data set, which is completely separate from the sample we measured. But we have all of these people's actual body fats, right? We can then cross-validate and say, using given measurements, we put this new cross-validations data set numbers, crunch them through our prediction model that we created with the regression, and we see how closely do the predicted values measure up to the actual values. And then we can figure out how good our regression model actually is. Okay. All right. As I said previously, outliers are bad. So we have to find a way for testing them. Okay. Our method that we're going to use is the box and whisker plot method. I explain this more in the activity, so I'm not going to go too deep into it, but it uses the interquartile range, which is the IQR, right? And we're going to be revisiting calculating quartiles 1 and 3. This doesn't work on all outliers, but generally it's a fairly good estimation of where outliers would exist, okay? There's also a method of distribution of residuals. We don't go into this in this class, okay? All right, the last thing, I kind of clumped assumptions together. So all of those slides that had the purple title, where it was like bivariate correlation, multiple correlation, bivariate regression, multiple and multivariate regression, this is where all of those assumptions are combined. So any correlations, we need to have random sampling. Both our independent and dependent variables have to be parametric. We have to have normality. Okay, so those are your 3 main ones. We also need to have a linear relationship, so straight line relationship, either represented by R, and again, not big R, but change this to B. Okay. And then lastly, correlations also have to have this funky thing called homoscedasticity. Everyone always trips over that word, and it took me forever to get it right. But basically, heteroscedasticity is the bad part. So homoscedasticity is what we have to assume is going on. Basically, this is looking at the residuals, or the distance, if you want to think in other words, distance of data points to whatever the line of best fit is. So in this case, if we look at this, you see this fanning effect, right? The residuals, or the distance of the data points, get further and further away as we go down the distribution. So that fanning effect is called heteroscedasticity. So we have to correct for that, or we don't want that in our correlation assumptions, okay? For regressions, same base 3, right? Random sampling, cat fight. Our variables have to be parametric, both independent and dependent, right? And then we have to have some degree of normality. Again, we have to have linear relationships where slope of our correlation is R, slope of regression is B. I'm just going to emphasize that. And then no multicollinearity, okay? Because that's where multiple independent variables have very similar correlation, right? Or have stronger correlations. So multicollinearity is added to our assumptions list for regressions. Homoscedasticity is added to our assumptions list for correlations. Okay. That was a lot. I understand. Do you guys have any questions? Okay. If you do, please don't hesitate to ask. I just did this lecture about 20 minutes faster than I have in the past. So, and I cut some stuff out. So it's a big thing. What I would recommend, again, look at all of the supplemental resources, go through those videos, review the lecture video, and then the activity, I would do that after you've reviewed everything pretty well. And that hopefully will make more sense when you're answering some of the more conceptual questions. Cool stuff.
Question?
Yeah.
So could you explain where it says the p-value indicates the significance of the relationship, not the strength?
Yes. So that was back in back in the correlation part, right? Nope, that's not it. Hold on. Here it is. I just want to make sure I'm sharing so that everyone's looking at the same. Hold on. Back to this part. This slide?
Yeah.
Yeah. Okay. So when we're looking at the significance of R, okay, R represents the correlation coefficient. Okay, so within that coefficient, we have some numerical value between 0 and 1 or 0 and -1, right? That numerical value tells us the strength. So example being when we look at, hold on, let me slide through here. When we look at stuff like this, right, where this R value represents the strength of the correlation. So it's going to tell us how tightly are these data points clustered together. The direction is indicated by if it's positive or negative, right? So you can see there's inverse direction. P is completely different from that coefficient in the respect that it's telling us, is the relationship significant or not? So that's what I mean by significance versus strength, right? Because strength is going to be indicated by R, or strength and direction are going to be indicated by R. So let's say we have a R value of 0.69, okay? Generally, we would say that would be moderate to strong, right? A positive, moderate to strong relationship. And then if P is, or if on your correlation matrix in SPSS, it's tagged as P is less than 0.05, that just indicates that relationship is significant, okay? Sometimes you can have weak relationships come up as significant. Sometimes you have strong relationships come up as not significant. It kind of just depends, but the significance doesn't tell you anything about the strength of the relationship. That's the main thing, is that significance and strength are independent of one another. Did that help answer your question?
Yeah, it makes sense.
Cool. Any other questions? Okay, so you guys are rock stars. You stuck it out. Watch everything. Email me, office hours. We can set up extra office hours. I don't care. I am here for you. Okay. So good luck with working on everything for this week, and I'll see you next week.